Hello, this is T Chapman 500, and this is the complete instruction set that I've updated for my original CPU, at least what I have so far. So all of the original functionality of the original CPU is in here, as well as some functionality that I intended to put in. So if we go into the Logisim like we've done here, we can see that I've been a little bit busy. So we have 3 address registers in this block here. One for the stack. This was for storing data on the stack for functions and various other things. We have the pointer register. We also have the program counter. We have the temporary address. We have the instruction register, and I did not mean to bring that down. The instruction register, not instruction address. The temporary register, which was the accumulator, the arithmetic logic unit output, and of course the arithmetic logic unit, which, by the way, the original arithmetic logic unit had a multiplier implemented in the original. This one does not, so I'm not sure if I will put the multiplier back. I really don't intend to do that, but it can be done. I do have the instructions for it, and if we take a look here, I have 2 instructions left over, one for multiply and the other for divide. Let me interrupt with a little bit of post-commentary. The multiply instruction will be present in the final design, but the divide instruction will not. I've also updated the instruction listing that you've seen so far. Back to non-post-commentary. So we can do multiplication and division, and then have another instruction for transferring whatever's in the upper half of the result to the output register. Post-commentary again, just to be clear, regardless of what you hear in the sections that are not post-commentary, there will not be a divide operation. There will, however, be a register to separate the lower and upper half of the multiply operation. Back to the video that I've now interrupted twice. So we have 3 instructions implemented, plus the instruction loader here. The no-op instruction is instruction 0. Call is opcode 1, followed by the address. Lower portion of the address first, then the upper portion. And then we have the return instruction. And actually, I think I'll move this over a little bit, so it's not so close to the edge. Opcode 2, 3, 1 byte. And since I botched the recording, I might as well show you what's going to happen. I'll go through this slowly, so we can see the signals here, which are set to get the data out of the RAM and into the various locations. So we do the clock, and the program counter increments quite nicely as we load the data into this register. And then finally, we call our function, which the size of this function is 1 byte. And it's a return instruction. So if we do this, it just sends us back to where we were and loads the next instruction, which is a no-op, which does nothing. The no-op is also the fastest instruction, taking only 1 clock cycle. The other instructions take at least 2, and in the case of the call function or call instruction, in the case of the call instruction, 1, 2, 3, 4. And of course the return instruction takes 2. Oh, let's see, 1, 50, 10, 1, 50, 10, 1, 50, 10. Just because I can. And it'll be interesting to see how this works. So So let's see. Yep. Okay. Yep, that works. And there we go. The RAM's cleared, except for this one, and the return instruction later on. So 3 instructions implemented so far. And everything that you see here is going towards the goal of making this CPU as functional as I intended before everything broke. And I do have a video on the original CPU that is broken and probably no longer exists. You can go ahead and check that out. I will put a link to that, I think, in a card if I can, otherwise it'll be in the description. Anyways, let's check out how this works. First, the stack pointer. This part of the circuit will increment the stack by either 1 or 2, or decrement the stack by 1 or 2. This holds the stack error flag in case we do an underflow or overflow. This gives us the bounds of the stack, so this is always the bottom of the stack. This is the highest that the stack can go. And the address goes from the bottom of the stack being the highest address, the top of the stack being the lowest address, so it's quite sort of backwards compatible with the Intel processors. Then we have the address out, and if this thing ever goes beyond the bounds of this, then we get the stack error flag raised. So this is what actually checks for the stack error, and this is what locks the error into the register, and this would just halt the CPU altogether. So this right here gives us 1 kilobyte of stack data available. I don't think we'll need any more than that. Oh, and we have to do something special to initialize the stack. So if we were to do this, we can set this here, write enable, so the reset and write enable will put the 4096 into this register. We clock that, and that's the complete initialization of the stack. We set this high and set this high to initialize the stack, and I have an instruction in the instruction set, if you go back and pause the video, for doing exactly this. It should be the first instruction called. At least the first instruction called if you use the stack, and if you also use the interrupts, which will be later in the series, then you initialize the interrupt lookup table as either the first or second instruction, with the stack pointer being the other instruction. By the way, you don't have to do that first, as long as they're initialized before they are ever used. So let's take a look in the pointer register, and this part will allow us to increment or decrement the register by anywhere from 0 to 255. So this is essentially a pointer arithmetic, and this gives you the ability to set an address into the pointer register. This is the actual pointer register. This is the output, which we can set into the data bus. So if we go to the program counter, so this is the call stack for the program counter's dedicated call stack. There are 2 call stacks, one for the program counter, the other for the data, and this is what's on the stack, and this doesn't reset when we reset the other stuff. So this circuit here is for managing the stack, and as you can see we have the stack error available, which will trigger if we have a problem here. So if it loops back around to 255, it'll throw the error, and if it loops around from 255 to 0, it'll throw the error. So this is how we get data into the program counter for stuff like jump and call instructions. This is the complete control for the program counter. And this just manages where all the data goes. So if we go into the stepper, it's just a basic counter with a single output and a couple inputs. Going to the temporary address, we have an 8-bit data line going in, and we can trigger the write enable for the lower half and upper half individually. By the way, the lower half should always be loaded first. And then the instruction register, pretty simple. The temporary register, if I can get into it, again, pretty simple, with two outputs, one to the data bus, the other to the arithmetic logic unit. The output register, again, pretty simple. If we take a look at the instruction loader, that looks pretty simple there. We just have a comparator checking if the step is 0, then we send all the signals that we need to send to get the instruction loaded. Take a look at the call instruction. It's a bit more complex, but what we have here is a comparator and a stepper to enable if the instruction is correct, and then the stepper to select which one of these things. And on the last step, we just clear the stepper. Same with the return instruction and the no op instruction, except the stepper clear is on the first step. And finally, the arithmetic logic unit. And I showed you this in the first video. Nothing's changed here. We have the flags. We have the logical operations of and, or, not, XOR. We have shift left and right, negate, increment, decrement, add and subtract. And that's it. So I was going to sort of show you the process of wiring up these things, but the recording got corrupted. So I'll just leave you off here. I hope you enjoyed the video. Please leave a like if you did. Don't forget to subscribe. And also check out the gaming channel for gaming related content. If you want to support this channel, you can do so on Patreon, PayPal, or Subscribestar. And in the next episode, I intend to implement a couple other instructions. This is T. Chapman 500 signing off. Hey, I see you stuck around to the end of the video, so I'm gonna explain this Proc 16, and if you already paused the video to figure it out, good for you. Let's get to explaining it. So first off, what you want to do is push the data to the stack. So the upper half of the B input, followed by the lower half, followed by the upper half of the A input, followed by the lower half. And then you call this function. The function assumes that you have registers 0 and 1 available for writing, as well as the temporary register. You really shouldn't be calling any functions when you have the temporary register currently in use. So 3 registers are assumed to be available. Now, because this function needs to use the pointer and output registers, it first pushes whatever's on those registers to the stack to free those up, copies the stack pointer to the pointer register, and gets the first argument, which is this thing, the lower half of the A input. It does a little bit of pointer arithmetic, loading this into register 0. Then it gets this thing, loads that into the temporary register, adds that, puts that into register 0. Then this will get this part, followed by this part, putting the A into register 1, B into the temporary register. We add with the carry, setting the result to register 1. So the return value will have the upper half of the result in register 1 and the lower half of the result in register 0. And finally, since we're done, we just put the original data from the stack back onto the respective registers in the reverse order that we put them there. And then we hit the return. This should be followed by 4 pop instructions, since you made 4 push instructions to get this onto the stack. Oh, and this circuit will be available on GitHub.